Hello everyone. In this video, I will show you how to design a multi-image boot bitstream with Xilinx FPGA. For various reasons, you may need to save multiple bitstreams in the FPGA boot flash memory, for example, infill upgrade, or call out different FPGA functions based on some conditions, etc. Then you select one of the bitstreams to be active and boot into it. Xilinx FPGA has built-in bootloader mechanism and warm boot vector in the bitstream. The multi-boot feature enables the FPGA to selectively load the bitstream from a specified address in the flash memory. We will take a look in the details in a moment. Previously, we have talked about the Intel Max-10 multi-boot functions. It's internal flash storage and works a bit different from Xilinx method. In this video, we will try to replicate the method showed in Xilinx application notes 1191. Please note that the application notes is aimed for ultra-scale devices. We will also take a look how to migrate the design to 7 series device. We will use Xilinx KC705 for the demo. In XAPP 1191, Xilinx showed this system diagram and detailed step-by-steps of loading each bitstream into flash, trying out good or corrupt bitstreams, etc., and boot and fallback, etc. The application notes is mainly for explaining SPI programming feature via the HDL code. Personally, I found that the multi-boot section in this document is not very well explained. This is how the multiple bitstreams organize in the SPI flash, and here is the simplified version. Basically, this is a small warm boot sector at address 0. In that, it contains the warm boot vector, meaning the next boot to address, then jump to that address and continue boot bitstreams from there. In this demo, I will show you how to boot to one of the two functional bitstreams based on the dip switch on board, the status at power up. This is how the selective boot mechanism. So the board power up and SPI flash boot from 00. In that warm boot area, there's a boot vector. So the bootloader reads the warm boot address and jump to either 00A or 00B SPI address and continue loading the bitstream there. In each of this bitstream, when the bitstream load, it first exercises the dip switch. See in this lower section bitstream, the function is that if it sees the dip switch pin is low, then it will continue boot to the main function of this bitstream. If it sees the dip switch pin is high, meaning the user trying to boot to the higher section of the bitstream, then it will execute the SPI write process and change the warm boot address in the warm boot sector, and then issue a reboot. When this reboot, it will go to the higher address bitstream. In the higher address bitstream, it has the similar mechanism. At boot time, it will exercise the dip switch pin. When it sees the dip switch pin high, it will remain in this bitstream and activate the other functions in this bitstream. Otherwise, if it sees the pin is low, it will change the warm boot vector back in here and issue another reboot. Goes back to the warm boot and go back to the lower address bitstream. The whole demo includes 3 separate projects. Project 1 is the base project that serves as the warm boot sector. There is basic functions like LED flashing, etc. All source codes of these projects can be found in my Github. I put the link in the video description below. In reality, this FPGA features is not even needed, but we will build this project mainly to expose the basic warm boot vector jumping binary. The bitstream config of this project is set to enable warm boot, and the next boot address is set to 200K. Now we will build this project. As you can see, this is a very basic function, only toggling the LEDs and showing the dip switch status in two of the LEDs. Now we also convert the Bitstream to the MCS file that can be loaded directly into the SPI flash. So you can see we will load the Bitstream at 00 address. If we look at the MCS file, here is the first several bytes. To understand what these bytes are, we can reference to Xilinx configuration user guide from UG470 for 7 series or UG570 for ultra-scale devices. There is Bitstream examples in the user guide. You can compare these bytes with this. As you can see, this is the synchronized detection, bit width detection, synchronized byte. Not used, and then some commands set to here, and there is explanation of all those bytes, what they're doing down below. Configure package, what the codes are, etc, etc. As you can see, the very important 4 bytes serve as the warm boot. It's that this command right indicate there's a warm boot start address, and this is a reserve address. We can find this 30020001 here, 30020001, and then this is the boot address that we set in the Bitstream configuration, 00200000, the warm boot address. And then is the command sent to the command register. On this example, Bitstream is 0. In our case here, it's 0f. We can look what the command 0f is. Command register code. 0f is I program, internal program for trigger a warm boot. So basically this is the warm boot command. First set the warm boot address and then trigger the command. Now we can load the Bitstream to the board. We will add the configuration device here. This is what's on the KC705 board. On the KC705 board, remember to set the dip switch here to boot from SPI, and also you will need the jumper here. If you look in the schematic, you will see that this jumper enables the internal SPI flash. Without the jumper, it's booting from the SPI connections here. Now we will load the Bitstream to the board. We can verify what's on the SPI device. From 00, if we read some of the bytes here, as you can see, it's the same as what we programmed in. It's jump. The instruction is jump to 200K and reboot. But if we read the 200K address, As you can see, there's nothing there. So because the Bitstream configuration here, we enable the Bitstream warm boot and jump to the SPI address 200K, and we don't have anything there at the moment, so it's just like a upgrade process but fail with the upgrade SPI write. When the Go image boot, it jumps to nothing, and because we have set a timeout, so it will eventually go back to this base feature Bitstream and boot itself. This one will show not programmed because it doesn't see any Bitstream in the 200 address. And once we refresh, it's actually programmed with the same Bitstream. From the LED, you can see this is what we design in the Bitstream, the LED flashing, and also with the 2 bits showing the dip switch. Now let's look at project 2. In this project, other than the basic functions like LEDs, we also add the SPI write function from the XAPP 1191 version select feature. As you can see, we send the dip switch into that, and at power up, the code check the pin status and decide whether it's going down to idle or continue use the SPI write function and load the memory to the warm boot section. So in XAPP 1191, the HDL codes are actually for ultra-scale device. When using in 7 series device, some of the Xilinx components needs to be changed. For example, this SPI programmer feature, it used the built-in start function. On the original XAPP 1191, it used the start E3. In 7 series, we use start E2, and some of the pins or functions are different. In this start E3, all the SPI pins are actually built in the DIDO here, but Start E2 doesn't have that. Start E2 only include the SPI clocks. So we need to manually latch the clock in negative edge and then use the tri-state control to control this in and out buffer. The SPI erase and program feature also slightly different in the application 1191. The ultra-scale boards use the newer SPI device that supports the 4-byte mode, but in KC705, the SPI memory doesn't support the 4-byte, so we bypass the 4-byte mode feature and directly go into erase, use 3-byte or write into 3-byte. The application node is also mainly for demonstrate how the warm boot jumping is designed. The code actually is not very robust. This SPI write feature only triggered by the FIFO full. In any case, the FIFO is not ready and glitch with the full signal. The SPI write actually write some 0 bytes to the warm boot sector, which is very dangerous. When we create this demo, we experience several times the warm boot sector is all erased by 0 and break the boards. So we put some improvement codes here to gate the SPI write. Only when this successful erase sector finished, we can let the SPI write continue. Other features like the FIFO 36 is also different in ultra-scale device and 7 series. So in ultra-scale, it uses FIFO 36 E2, but in 7 series it's FIFO 36 E1. And by default, the FIFO 36 E1 component could not do bit width change between data in and data out. We have to create a wrapper component to enable this. The Bitstream that will be written into the warm boot sector is also slightly different. If we compare the bytes used for the ultra-scale device and the bytes used for the 7 series, you can see some of the features are lost support in the 7 series. That's another reason we built the Multiboot project to just expose the bytes that we are going to use in the project 2 and project 3 to be replaced with the Multiboot setter. This DRAM to flash section that we are going to write into the Multiboot setter is completely using the bytes from this project 1 demonstration. So the second project includes this version select feature, check the bits, and write the SPI flash and call this iProgram function. Also keep in mind that in the application 1191 it used ICAP E3 and here we use ICAP E2. Now let's build the project. Now we will create the MCS file with both the Multiboot setter at 0 and the project 2 at 200k address. And we will program that into the board. Now, when we reboot, it should go through the Multiboot setter and jump to the 200k address with the project 2, which the LED just flashing slowly. As long as we keep the dip switch low, the SPI write feature in the project 2 will not be triggered, and we can put as many times as we want. Now, if we put the dip switch to high, it should go to the Multiboot setter and jump to the project 2, and project 2 will read-write the Multiboot setter with the higher address 400k, but without anything there, the FPGA will boot to nothing. As you can see, it will show nothing over here. And the FPGA is not programmed. Now, if we read back the Multiboot setter, we can see the Multiboot setter is replaced with the second block in the SPI to flash block. The address is 400k to boot to, but we have nothing there. Now let's look at project 3. Basically, it's the same as project 2 with small changes. For example, let the LED toggle a faster rate, and in the version select block, we will exercise the pin's status. Dip switch pin is at 0. We will rewrite the Multiboot block. Otherwise, we will just keep going and idle in this section. All the other codes are identical from project 2. Now let's build the project. Now we will create a complete MCS file with all 3 bit streams with Multiboot setter at 0, project 2 at 200k, and project 3 at 400k. And then we load this bitstream to the board. Now, here is the final look. When the dip switch at low, the board will boot to project 2 with slower moving LEDs. When the dip switch at high, it should boot to the fast moving LED in the project 3. Project 2, Project 3. This is the whole demo. Remember that this method needs to write to the SPI boot sector address 0. So it's okay to demo how the warm boot is working, but it's a bit of dangerous. In any case, if the write is broken, the board is easily break. You have to use the JTAG to reload the board. So in reality, use this method should be very careful. Next time, we will look at another more secure way to multi-boot. Hope you enjoyed the video and see you next time.